What motivated Newton to develop calculus? As you probably know, it was the study of the movement of the celestial objects. In particular, he wanted to know how the planets moved around the sun and also how the moon moved around the earth and so on and so on. But the functions we have used so far pose a problem when it comes to analyzing the movement of the planets, because the functions that we see have usually a graph that looks like this. But this doesn't look anything like the movement of a planet around the sun, which looks more like something like this, where the planet would go round and round, as we know, in elliptical orbits. So how are we going to adapt to this situation? And that's where the idea of parametric curves comes in. So let's have a look at what parametric curves actually are. Here is a definition, or more likely description. I'm not going to be too formal in it, but let me remind you that a function is a relation of the form y equals f of x. What does that mean? It means that we have a relationship between two quantities, an input quantity that we call x and an output quantity we call y, and that's described by some kind of formula or rule that allows us to go from x to y. So by using a simple example, we may have a parabola like this, and then for every x, we generate a corresponding point on the curve, which will have a coordinate f of x, and then together they will identify a point x f of x. Now, what we're going to do with parametric curves is we're going to describe the two variables separately by using an even third variable, which is referred to as the parameter. And it's usually denoted by the letter t. Why t? Well, because traditionally this is going to be a variable that will describe time, although that doesn't have to. Okay, but originally, historically, that's what it represented. So what we do is, instead of representing y as a function of x, we represent both x and y as functions of these t. And in fact, quite often a parametric curve can be represented by two equations which specifically identify x as a function of t and y as a function of t, right? So in this situation, so what we have is, instead of having for each x a corresponding value f of x, for each t we have two corresponding numbers, x of t and y of t. So for instance, if x is equal to 0, we might have this particular point x of 0, y of 0. And then for 1, we might have x of 1, y of 1, and so on and so on. Or more generally, we may think of the point as moving on the curve, being driven basically by this parameter t. So as t changes, x and y will also change, but still they're being related to each other and they will follow the curve. By the way, these curves are also sometimes called the vector functions, and you're going to discover later why, but we're not going to dwell too much on this point, just a little bit of curiosity. This is actually an extension of the concept of a function. So the idea of parametric curves is an extension of the concept of function. Why is it an extension? Well, because every function can be written in parametric form. If I give you any function of the form y equals f of x, I can use x itself as the parameter and then write x as being t itself, and then y as being f of x, which will then be f of t. So every function can be written in parametric form. However, not every parametric curve is a function, because they may not pass the vertical line test. For instance, look at this parametric curve. By the way, you may want to discover on your graphing calculator how to input parametric curves and how to graph them. Most good graphing calculators will allow you to do that. So you can check on your calculator what this thing looks like, and it turns out it looks like that particular ellipse that I was showing you earlier. So in this case, of course, this is not a function, so there's no way that I can write this curve as a function, but I can write it fairly simply as a parametric curve. So what does this do for us? I've already said that it allows us to describe curves which are not functions, that do not pass the vertical line test, but they actually do quite a bit more. It allows us for more options, even when we're dealing with usual functions. As I've just said, the usual function can be represented as a parametric curve, and this gives us some advantages. For instance, first of all, if we have a parametric curve, we can identify something called the starting point. And this basically corresponds to the point for which t is equal to 0. Think of t equals 0 as the starting time, now, right? And so we can think of that one as a starting point. So for instance, if I have the function y equals x squared minus 2, it is a simple curve, and yes, it has intercepts, but didn't seem to be something intrinsic to the curve. Okay. Now, if I represent this curve in parametric form as t and t squared minus 2, so just in the general form t f of t, then for t equals 0, I end up with the point 0, negative 2, which of course is the y-intercept in this case. But we're looking at it as the starting point of the curve. But I can change the parameterization. I can write that same curve as t minus 1 and t minus 1 squared minus 2. In that case, the starting point will be at x equal negative 1. So I can choose a starting point if I have to. Another one is that I can choose different orientations. Normally with functions, we always go left to right. We draw them left to right because we write left to right. But with parametric curves, we can go left to right or right to left. Or sometimes we may have other options depending on what the curve is. For instance, back to our basic example, if I use the basic parameterization, my curve will be described left to right. Why? Because as t increases, t being the x-coordinate, then the x-coordinate increases and goes left to right. But I can write the same curve with a different parameterization as negative t and t squared minus 2. Of course, the y is the same because if I square negative t, I still get t squared. In this case, as t increases, negative t, which is the x-coordinate, will decrease. And so my curve will be traced right to left instead of left to right. Now let's see what happens when we have our good old ellipse. I can use this parametric form for the ellipse, which is the one we've used before. And if you actually trace this curve on your graphing calculator or some kind of computer program, you will see that it will trace the curve counterclockwise. But I can change the parameterization. This second formula gives me the same ellipse, just in the opposite direction, in clockwise manner. If you don't believe me, just check it. Don't worry too much about proving that, in fact, those two give the same curve. So this is another advantage. I can change the orientation, go left to right, right to left, and for more complicated curves, I can choose all kinds of other different orientations. Also, we can use different speeds. Once again, when I look at a function by itself as a function, it's just a static curve. Beautiful picture, but no more than that. But if I think of this as the orbit of a planet, or just more simply the trajectory of a moving object, oh, and by the way, this is another very good application of parametric curves to describe the trajectory of some moving object like a satellite, a car, or anything. So if we describe that curve in parametric form in the standard way, then it will go left to right with a certain speed. As t increases, x increases exactly the same rate as t, and it goes like this. But let's say I look at this particular parameterization. So I change t to 4t, and correspondingly, of course, the y will change from t squared to 16, which is the square root of 4 times t squared minus 2. Now in this case, the thing will go faster. Okay, let's look at it again. So if I look at this parameterization, we'll go 4 times faster, so we will trace the curve much, much faster. Okay, so that's another advantage. Also, what we can do is we can use a parameterization to select a certain section of the graph. So if I look again at my basic curve, x squared minus 2, I'm looking at the whole parabola going all the way from negative infinity to infinity. But for some applications, I may only want a chunk of that parabola. And so what I can do is, instead of using the standard parameterization, I can use this one. Again, notice that the y-coordinate here is equal to the x-coordinate squared minus 2. But the x-coordinate, now being cosine of t, can only be between negative 1 and 1. And therefore, I'm shrinking my curve to only the section between negative 1 and 1. So, lots of other options that are available to us by using the parameterization. However, in some situation, we may want to do the opposite thing. So in some situation, we want to eliminate the parameter. What does that mean? What it means is that we start from a parametric curve and we want to identify some relationship which links x and y without using t. So let's see how that can be done. For instance, let's say I'm starting from this parameterization. So in this case, what I know is that the x-coordinate is equal to 2t. So that means that t is equal to x over 2. All right? The y-coordinate is 4 times t squared minus 2. But I know that t is equal to x over 2, so I can change the t to x over 2, clean up a little bit, and end up with this. Well, look what we got. We got a y on the left-hand side, then an x squared minus 2, and we're saying they're equal. Well, that allows us to create a general function notation which does not include now t. This can be useful in some situations, though not always, but you do want to learn how to do that. Sometimes in order to do that, we may have to use some formula, some identities, some particular thing that we know. For instance, let's look at this particular parametric curve, and you may want to pause here and input that in your graphing calculator and see what this thing looks like before I show you another way what it looks like. So what do we know in this situation? Well, we know that x is equal to cosine t plus 1 and y is equal to sine t minus 1. If I move things around a little bit, it turns out that the cosine of t is equal to x minus 1 and the sine of t is equal to y plus 1. But we know how sine t and cosine t are related for any number t, namely the Pythagorean identity sine squared t plus cosine squared t equal 1. So what I can do is I can change sine t to y plus 1, cosine t to x minus 1, move things around a little bit, and end up with this particular equation. So now notice once again that this equation does not have any t's, so we're back in the usual formulation. Notice also this is not a function. In fact, if you graph this one, or if you've studied something about conics in the past, you'll realize this is actually a circle. So by doing this, we can come up with an equation that links x or y directly without going through t. Once again, sometimes this is useful, sometimes it's not, and sometimes it cannot be done at all. But these are all useful things to know.